All right, in this video we're going to look at just square roots of complex numbers. So in the previous two videos we were just looking at roots which included square roots, cube roots, fourth roots as well we did. So this, if you like, is a bit of a subset of that video, but square roots are special because we can evaluate them using two methods. So in the previous video, we're strictly using the de Moivre's approach, where we express the number in a polar form and then we find the roots. Well, we can still do that for square roots, but we can also find square roots using the rectangular formulation. So this is how that method goes. So in this method one, we're going to use the rectangular formulation, so we don't necessarily have to convert the number to polar form first. So if we just let this square root be equal to a plus ib, where a and b are both real numbers, okay, then if we can find a and b, then we have found the square root of minus 5 minus 12. So what we're going to do is we're going to square on both sides. If we square on both sides, then on the left hand side we're just going to have the terms inside the square root. On the right hand side we're going to have a plus ib all squared. If we expand a plus ib all squared, it's going to be a squared plus 2aib, then plus I squared b squared. But I squared is negative 1. So this is the same as minus b squared. Then if we collect the real and imaginary terms, then this is what we have. On the left hand side we have got this. Now this is going to is usual with equations involving complex numbers. So at this point we balance the real components and the imaginary components on the two sides of the equation. So if we take the real components, for instance, on the right hand side we've got a squared minus b squared. On the left hand side we've got minus 5. Let's call this our equation 1. Then balancing the imaginary, on the right hand side we've got 2ab. On the left we have got minus 12. So we've got two equations, two unknowns. They are not linear, but we can surely solve them. So if we make b the subject of the formula in 2, then we're going to have negative 6 over a. Then we can substitute that into a, or into equation 1 rather. So we're going to have a squared minus negative 6 over a all squared. This is equal to negative 5. And so this is going to be a squared minus 36 over a squared is equal to negative 5. Multiplying through by a squared, going to be a to the power 4 minus 36 is negative 5a squared. So this is going to be a to the power 4 plus 5a squared minus 36. Now since this equation does not involve since this equation only involves even powers of a, this is just a quadratic in a squared, which actually we can factorize easily. So we need two numbers that multiply to 36 have a difference of 5. It's going to be 9 and 4. So it's going to be a squared plus 9, a squared minus 4. This tells us that either a squared plus 9 is equal to 0, or a squared minus 4 is equals to 0. However, the first one, if we try to solve the first one, it's going to give us a plus or minus 3i, but remember, a and b, we have restricted them to be real, so that means this one we have got to discard. This second one, if we solve, it gives us a is plus or minus 2, so that is the one that we're going to go with. If a is 2, then if we plug in 2 here, so b is negative 3. B is negative 3. And then if a is negative 2, b is 3. So we have our solution now. So all we need to do is just plug in a and b here. Okay. So this is what it's going to look like. So therefore, square root negative 5 minus 12i is going to be equal to, so it's a plus ib. So from here, there's going to be 2 minus 3i minus 2 plus 3i. Again, notice that this is the negative of that, something that we mentioned in the previous video. So that is the first method. So in the second method, of course, we're going to use the polar formulation and De Moivre's theorem and that formula that we introduced in the previous 3 videos. So method 2, so we're going to use the polar form. So we're going to take the number negative 5 minus 12i and convert it to polar. So these are the coordinates. So that tells us that this number is in the third quadrant. So this is going to be negative 5, and that is going to be negative 12. We need to find r and theta. R is going to be negative 5 squared plus negative 12 squared, all under root 25 plus 144 is square root 169. So r is going to be 13. For the argument, we need to find this phi. So phi is inverse tangent negative 12 over negative 5. So it's just inverse tangent 12 over 5. Of course, this is not going to be an exact angle because the two sides dictate that the angle is not a special angle. So theta is going to be 180 plus inverse tangent 12 over 5. So we're just going to keep it like that. We're not going to write it in decimal form, so that when we work out our answer, we find the exact root or the exact solution. So what's going to happen, therefore, is negative 5 minus 12i. We can write as 13 cis theta plus 360k, raise this to the power 1/2. So that's going to be square root 13 cis theta plus 360k all over 2. So if you call this rk, then we just run the values of k from 0. So when k is 0, this is square root 13 cis theta over 2. Then we punch this in the calculator. So the real component is going to be square root 13 times cosine theta on 2. The imaginary component is going to be square root 13 times sine theta on 2. So let's see what the calculator is going to give us. So the first thing we need to do, make sure our calculator is in the degrees mode. It is. So then we're going to do 180 plus inverse tangent 12 over 5. Okay, and so that is our theta. We are going to save this as b. Okay, so our theta is b. So for the x component, we're going to have square root 13 times cosine b over 2 equal, so that gives us negative 2. So negative 2. Then for the other component, going to be the same calculation. We just convert, make this one sine here. Close brackets. And that is going to be 3, so 3i. So that is the first one. Then for the second one, we are going to have now k is 1. So it's going to be square root 13 cis theta plus 360 all over 2. Okay, now remember our theta is b. We saved it as b in our calculator. So what we are going to have to do now is square root 13 times cosine of open brackets, b plus 360 divided by 2. Okay, and that gives us 2. So 2 here. And then we go back to the same calculation and we change this to sine this time. So we want sine okay, let's just do this from scratch. So it's going to be square root 13 times sine of open brackets b plus 360, then divided by 2, and that gives us negative 3. Okay, and this is exactly the same values as we found using the other approach. You're going to notice that this de Moivre's approach is going to be relatively shorter than the approach using the rectangular formulation. At this point, we're going to give you an opportunity to have a go at the second one. Just pause the video, have a go at this one, and then you can compare with our answers when you continue the video. Alright, we're now going to scroll down to our solution for part B. We'd like to thank you for visiting our channel and watching this video. We hope that our material is helpful to you. Please do not forget to subscribe to the channel and like the video accordingly. And if you've got any questions, we would like to hear them. You can post them in the comment section. Before we go on to part B, well, we just want to demonstrate that for part A, if this is the square root of minus 5 minus 12i, then when you square this, you must get minus 5 minus 12i. So let's see whether that works out. So when you square this, there's going to be 2 squared minus 2 into 2 times 3i plus 3 squared I squared. 2 squared is 4. 2 times 3i, that is going to be 12i. Then this is going to be 3 times minus 1. Sorry, the 3 squared is 9. So that's going to be 4 minus 9, which is minus 5 minus 12i, which is the expected value. Alright, so for part B, if we let this be a plus ib, squaring both sides, it's then going to give us these two equations if we match the real components, and this one if we match the imaginary components. Making b the subject of the formula here and plugging it in here gives us this equation, which can be simplified to that. Then we factorize. However, this one gives us imaginary value of a. This one gives us plus or minus a. When a is 1, plus or minus 1. When a is 1, b is 2. A is minus 1, b is minus 2. So that's going to be the square roots. Then using the de Moivre's approach, first to write this in polar form, r is going to be 5, because you can see this is going to be the 3, 4, 5 triangle. Then theta is going to be 180 minus inverse tan 4 over 3. Then if we punch this into the formula, so for the first one here, we have got square root 5 times cosine theta over 2, that gives us 1. And times sine, it gives us 2. And this is the other one. All right, thank you.